Here we go. So, represent and solve problems relating to exponential growth and decay. Okay, how many things are we all good? Yeah. Alright. First of all, we'll start with growth and then we'll do decay afterwards. I have no idea, internationals, if I say the word bacteria. Do you have any idea what I'm talking about? Yeah. Yeah, you do know the word bacteria, are you sure? Because if you don't, this is going to get real confusing real fast. Bacteria, you know what that's about?
Why is the word bacteria?
Because, yeah. Yes, no? No, okay, so at least some of you want to. Do you know what the. Wait, Cantonese or Mandarin? Mandarin. Do you know what the Mandarin word for bacteria is? Yeah, you know what I'm talking about? Yes, yes. You guys, yes? Yeah, you know that's not cool. You know what I'm talking about? You know the word bacteria, right? Yep, okay, good. You do know or you don't know? You don't know this one?
That's messing with that. I'm not going to the biology.
No, but yeah, so you understand that word. If you're asking me about biology, you know what that word means. Yeah. So there's the little things. Yeah? Yeah, okay, good. Right.
You just need to know the word.
No, I was saying about why are we asking about biology?
You'll find out.
Yeah, that's what this is. I'm going to use it to springboard from. So, what does bacteria do? Multiplies really well. Yeah?
Really?
Wash your hands. Right?
Wash your hands.
Good. So, let's say I'm going to use rod bacteria. That's my one bacteria. Right? After a short amount of time, what's going to happen?
That's what we're done.
Right, I'm going to get two of them splitting off. After a short amount of time.
4 of all.
After a short amount of time.
8.
Can't be bothered.
16.
12 almost happened.
32.
Right, what's happening?
64.
What's happening?
It doubles every time. Exponentially growing.
Fantastic. Alright.
2 to the power of X.
Right, let's say that this happens every minute.
Yeah.
Okay?
Very slow growth rate.
How many are there after 10 minutes?
2 to the power of 10.
Okay, so you've immediately nabbed it. Great. So, call this time 0. Right, this is time 1, 2, 3, 4. Oop. 3, 4, 5. 1 is 2, 2 is 4, 3 is 8, 4 is 16, 5 is 32. So they are all x squared. They're all powers of 2, right? So this is 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, etc. This is 2 to the 0, which is 1. Yeah? Great. I wanted 10. So that's going to be 2 to the 10, which you definitely memorised by now, because I've told you enough times to memorise some of these.
Well, I don't really
2 to the 10, what is it? Figure it out fast. Don't touch a calculator, think!
Isn't that 1,000?
1024, thank you very much. Easy one to remember, it's 10. It has 10 at the start of the number, it goes 1024. Oh, there you go, alright. Cool. Great, well, what if instead this took, let's say, 30 seconds to happen? So this is now 30 seconds, 60 seconds, 90 seconds, 120, so on.
Yeah.
And I want to know what's happened that time, 10 minutes.
10 minutes.
10 minutes has passed. Okay.
Oh, maybe 20?
That's 10 to the 20, right? Why?
Because 30 seconds is half a minute, so you're going to divide by half.
Cool, makes sense. Yeah. So this is half, half, 1, 1.5, 2, so on, so on, so on. Great, fine. Did that fundamentally change how these things were multiplying?
No.
No, it's just telling us how quickly they multiply. Okay. What if I want to fiddle with this a bit more? Now I'm going to say, okay, instead of starting with 1, I'm going to start with 5. How many are in this time period?
10, 25.
How many here?
20.
How many here?
40.
So on, so on, so on. How many are there at the 10-minute mark? Oh, suddenly that got a bit more fiddly.
13.
Okay, so let's think about this. Do you want to individually, for every worded scenario, have to go through this entire process?
No.
No, it would be nice if there was some general rule to deal with this sort of thing. So let's see.
X minus sign.
Alright, don't vote yourself. So, I'm going to start with some amount, and I'm going to end with some amount. So I'm very unimaginatively going to say I end with this amount at time t, and I start with some amount at time 0.
Yeah.
What's the amount going to be doing? Multiplying by, right, powers of 2, right? So I'm probably going to need a times 2 in here somewhere, right? Okay, how many times is this thing going to multiply by 2?
Yes.
Do the power n.
Right, n being,
The number
of splits.
okay, the number of times it splits, okay, fine. But what if I don't know how many times it's split, because all I know is how quickly they split and how long I've got?
In that case.
So let's change that. I need this in terms of time. Alright? Well, let's say that this thing split every minute. Right? What's t going to be measured? Right, minutes, right? Just t is the number of minutes. Right? If it doubles every minute, cool, just t is the number of minutes. What if it's every 30 seconds?
3t.
That was interesting. We all
T divided by.
t divided by 2. Okay, is that what we're saying?
Yeah, T divided by 5.
Let's pick a different time just so we don't have too many 2's floating around. Let's say instead this happens every 20 seconds. Now 20 seconds, 40 seconds, 60 seconds, 80 seconds, 100 seconds, etc. Okay. If this is going from once a minute to 3 times a minute, right, should my number be getting bigger faster or slower?
Faster.
Faster, right, because I'm dividing more.
So therefore, isn't it T divided by
times.
3T?
Okay. Because this thing is growing 3 times as fast.
Yeah.
Yeah, but people were shifting back and forth between 2t and t on 2, so we need to make it 100% clear. Great. Cool. Well, does anything else other than that happen? Well, all it does is you multiply by 2, so it's doubling, every however often. That's it. So it's a really nice short version of things. Okay, great. So for our version where we ask this, we could say, alright, I'm now starting with 5. I'm multiplying by 2 because everything's doubling. Right? I was told that we're going by 3 times a minute. And we've got some amount of time will equal some end amount at time t. Great. I specifically asked for 10 minutes, so okay. Times, that's a times, not a dot, like, not a decimal. Cool. So the amount at time 10 minutes is going to be equal to whatever that is. Alright? I do not expect you to do that in your head, but can you figure that out?
Yes.
Yep. Right. Given enough time, you can fit all around and figure that out. Great. Well, what if instead I told you, oh, I have 512 of these little things. They've been going for, let's write this down. So I've got 512 of them. They divide every, let's say, 10 seconds. Right, how many were there, let's say 1 minute ago? Okay, so I've got 512 of them. They divide every 10 seconds. I need to know how many of them I had 1 minute ago. What might I do? Okay, times becomes divided is one way to do things.
Turn 512 to 2 to the power.
Okay, we've got this general form. Use the general form, right? The only difference is this 3, we're going to change that to a k. Okay, because it's not always 3 times in a minute, it's some amount. Okay, great. So we've got the amount at 1 minute, oh sorry, at, how long we got? Yeah, the amount at 1 minute, well, we know that's 512. Okay, fine. We write our equation, amount at some time is going to be the original amount, which we don't know, that's okay, times by 2, because we're still talking about bacteria, so we're assuming they divide in half. Right, 6 times per minute. Cool. Great. Well, AT, well that's time 1, so we can put that in. Times 0, times 2, 6, what did we say, 1 minute? Yeah. Cool. Well, 2 to the 6. Oh, come on, how's it 2? 64, alright, it's got a 6 in it. Right, so we've got 512 equals AO times 64. Great, now what are you going to do?
Divide by 4.
Right. Anyone worried about doing that in their head?
Yep.
Shouldn't be. What are they both?
Powers of 2.
Powers of 2. This is 2 to the...
9.
This is 2 to the... Cool, equals...
2, 3, 8.
Done. Know your powers. I've been telling you since last year, possibly since year 10. Beautiful. So the original, not the original, the amount 1 minute ago was 8. Great. Well, that's nice and boring. It makes sense. Yeah? No? Yeah? Sure. The best thing is, you don't have to work through that every time, right? We work through it off of this one scenario, but we don't care anymore because we've got this nice generic thing. This guy, the 2, might not always be 2 though. It's for bacteria, it makes sense that it's 2, they're dividing in half. But if it's something else, it might not divide into 2s, it might divide into 3s, 4s, whatever. Right? So we've got a little bit of trickiness to get rid of that. Do I want to do that first or do I want to do that next? No, I'll do this first and then we'll do that last. Okay. Cool. If I say radioactive decay, English people will definitely understand, but radioactivity, radioactive decay, yeah, you know that stuff? Yes, yes, no. No. Do you know what it is in, did you say Cantonese or Mandarin? I can't forget. Mandarin.
I don't know.
Don't know how to explain that one. I might just look this up because it'll be easier.
Hey, sir. Find radioactive layer. That's all I'm doing.
I have no idea how to say that. Yeah, you know this. Always know this. You guys do this side? Yeah? Okay. Alright. Yeah. Oh, yeah, right.
We need just like a handheld translator.
Maybe? I don't know. Yeah, you know that, yeah? Beautiful. Okay. So, we've got 13, 14, carbon 14, almost down.
Oh, cool. Yeah.
It's self-amplifying broken walls. Is it? Have you memorized that?
Yeah, I think that's right. It might be a 3, but no, I think that's right.
What if I keep my box closed and don't even open it? I will definitely not box it.
For simplicity, let's get rid of that. Let's make it 5,700. So, for all the chemistry people, well actually no, all of you should be able to read at least this much science stuff. What does that say? Carbon 14, what does this say? What does that mean?
It lost the weight.
It lost to neutrons, we don't do enough science, okay.
There we go. I mean, it is it's not physics.
I understand that,
Stay continuous, otherwise it will change the
Okay.
properties of it.
but how many protons are in carbon?
12.
Whoa! That's friggin'
Hang on, who does chem? Oh geez, you do chem and you tell me there's 12 in carbon? That's a problem. How many are in carbon?
6, isn't it?
6.
Oh, yeah.
If you're doing chem and you don't know that, I'm really worried.
Yeah.
You should be.
Yeah.
No, I'm a scholar again.
This is carbon 12. How many protons?
6.
Right, it's still carbon.
Yeah.
Right, so the protons are the same. Right. Do these include electrons? No, right, you don't include them in your count because electrons are like roughly 1/2000th the mass, so they never end up being significant, pretty much. Cool, so how many neutrons must be in there?
18.
How many in here?
6.
Beautiful. Okay. So, when this guy decays into this guy, you end up losing 2 neutrons. We're not going through the details of what kind of radiation or the rest of it, we're just saying these turn into these, right, periodically. Now, the nature of that is purely inherently random and quantum mechanical, so we don't have to worry about details. All we're worried about is these turn into these. Half of them will turn into these every 5,700 years, roughly. Okay? Great. So, let's say I started with 1,000 carbon 14 atoms. Okay? From there, after 5,700 years, how many do I have?
500.
500. And after another 5,000, so what's this? 10, 1, 4, 0, 0. After that long, how many do I have?
250.
250, right? They're halving, right? It's not 500 and then 500 again and they're all gone. It halves every time. Cool. From there, what's this? Yeah, I can't even add 7100. I think that's right. 125, hopefully. Right, and then we can keep going again. And the numbers get progressively more upward. Great. Well, this is all well and good. Intuitively, do I have to wait 500 years before any of them will decay?
No.
No.
No, right? So they're going to be decaying all through this time. It's just when you get to, 5,000 years, I should say. So when I get to 5,700 years, 500 of them will have decayed.
Is that definitive?
It depends how definitive you want to be.
What do you mean?
50 less.
I'm going to say yes for this subject. And for all that you care about for this year, yes. Right? Is it? No. But yes. Yes, with an asterisk that I don't care to get into the technicalities of statistical mechanics for. Okay. Cool. So this thing is slowly decaying over time. Out of curiosity, will you have more decays, call this year 0, will you have more decays in year 0 or in the year 5,700?
0.
Year 0, right? Because more of them are there. So you'll have more decays and then it'll slow down, slow down, slow down, slow down, slow down, slow down. Right? Beautiful. I would like to know what happens in the year 1 million. You'll be dead. That's true. I want to know what happens to the carbon. No offense, I don't care about you being dead. I care about the carbon. Well, let's think. Maybe we can put this into some sort of general formula. We'll have the amount at some time later, which will depend on the original amount, timesing by what? Half, right? Because I'm halving everything. Cool. I'll have some, depends how long factor for each halving, times some amount of time. Brilliant, okay. What year did I say? 1 million, geez, okay. Let's make it 100,000 instead, just because otherwise this is going to get really stupid. Even that's pushing it. Let's go 50,000.
Why do you make 57,000?
Oh, fine, 57,000 anyway.
I'm just saying, I make it busy.
Okay, we'll do that. Yep. Cool, beautiful. Alright, so I can chuck stuff into this. AT at 57,000 equals A0. How much is A0? 1,000. The amount in year 0, whatever that is. Cool, half is constant. K, what's K going to be?
Oh, wait, no,
1
5.
over 5,700.
Perfect, this whole thing is going to be that. Why is that?
Because
You're falling down the cruise.
Right, I need this number to get up to 5,700 before this becomes 1, which would give me half of the original.
but then we're doing it in years this time, not minutes.
We are doing it in years this time instead of minutes. Does that matter?
Not
No.
No, right?
As long
You
as
just got to
both
keep
of
track of
them
your
are
units, right? In methods, you don't have to keep things in SI units. If you are welcome to turn this into SI units,
That's
you're going to want to
Enjoy
choose,
seconds.
right? Because you're going to have to do scientific notation. You're going to have to times by 24 and 3,600 and so what's that going to be? You're going to end up with way more figures than you need.
Yeah, no, I get
It's going to be terrible. You'll end up with like 4, maybe? I'm not sure. Yeah, you'll end up with 4 figures under there in scientific notation, which is now a power as well. So now you've got powers with powers that are fractions. So keep it in nice, easy units wherever you can.
Yeah.
Okay, cool. So we've got that. Brilliant.
Now in T, don't we put the 5, 7...
Yeah.
No, mind, go.
57,000, so this guy.
Yeah, that's what I was saying.
57,000.
Ah,
Great.
7,000.
Cool. 57,000 over 5,700. 10.
So 1 over 1,000.
Hey. Right, this. Cool. So very roughly, how many do I have left? 1. Slightly less than 1. Right, so it took 57,000 years for me to go from 1,000 atoms of C14 down to 1. Cool.
That was quite a few human lifespans.
Yeah. Beautiful. Are these formulas really similar? Yeah, they're really similar, right? Would it be nice if instead of 2 we could have 1?
Yes.
Yes.
Okay, well let's do this. Shuffle that.
Negative that.
2 to the negative 1. Move the negative up here. Hey, we've got 1. It's just K is negative if you're decaying. K is positive if you're growing. That's it. It's the only difference. Exponential growth, exponential decay, it's just a negative. That's the only difference. Cool. Next thing we want to generalise. Well, we've got halves and doubles. But what if we have 3s or 5ths or whatever else, or pies or anything? Well, that's inconvenient. Also inconvenient is running calculus on this. So what would you like to have in there if you're going to run calculus on it? What's the best thing, if you're involving powers, what's the only power that you can derive nicely? Sorry, the only base that you can derive nicely? 0? No.
X.
No.
1.
1, okay. If you have 1, is it going to grow? No, so that's no good to us. So good try with 0 and 1, but unfortunately that 0 means that the stuff disappears, and 1 means that it just stays constant. So try again. What did we do either last class or the class before? E. You want E. Why do you want E?
Because then, like, the area of the graph is the same as that, which is the same as that, or something like that. I don't exactly remember, but I remember that.
The root is equal.
Oh, yeah.
That's good. Yeah. Look at how easy that thing is to derive. That's really beautiful. That saves you a whole lot of garbage work. You want things in terms of E, if you can, if they're growing or decaying. Well, now we've got a bit of shoving around to do. How can we switch this around? Well, let's replace this. Keep A0. I'm going to keep this. I'm going to get rid of this negative actually, sorry. Because K could be a negative number. Yeah, so it could be either way. So I don't care about that. I want to shuffle around this 2, but I want it in terms of E. Alright, so I've got 2. How can I bring that in terms of E? Well, if I go log base E of E squared, that would be 2, right? Alright, so maybe we can fiddle around with this a bit. So we go log base E of E squared in there.
What happens if it's not decaying by half or doubling by 2? Then what do we do?
So you you'd have to change out this number depending on what that was every
Yeah.
time,
Yeah,
which
but
we'd
I'm
like to avoid. So,
Yeah, I mean, like in the log situation.
What if you have log E of E square,
No,
to
so-
the power of 3?
okay, I'm gonna generalise to that once we get there. But yeah, you're thinking the right way, so that's good.
Yeah.
Cool, this thing, okay, great. Well, what am I going to do now? I totally forgot what I was going to do. Good. I wanted to change this, and this is going to go up. That's going to go to there. So good. I forgot what I was going to do.
So I think it comes out of it. Can't surprise you?
No, just a lot of this.
You don't care?
The one else is going to get corrected, so that's.
Lost my train of thought. I should have written this on the side so that I wouldn't forget. This, yes, that's fine. So I don't care about this, I can jump in. That's fine. Oh no, it's up there, that's not, yeah.
What's this?
This, I can jump out the front. This one.
I don't know.
Oh no, that's just hanging back there.
Probably just be
the other one.
I'll send to Alex.
The long and the short of it is, you get down to e to the kt, where this k, make a k star, start here. You end up just changing that power there, which make that ln. Now, in general, a at some time t will always equal e to the sum kt. So regardless of whether you're growing or decaying, right, this will always be usable. Okay? The fiddly thing is figuring out what k is. Everything else in here, that's a variable, that's a variable, that's a constant, that's a variable in your function, right? Oh, sorry, actually that's a constant. Just for whatever scenario you're running. So for us, if we go back to whatever we go back to, this guy, we've got original amount, we had, we'll do the green one, 5, so that stays the same. End amount for whichever one we had, let's go time flow, let's see if it's time 2, we've got 20, okay? So 20 dot e to the k 2. Alright, we can solve for that k. So we've got divide 4 equals e to the 2k, ln of 4 equals 2k, half ln of 4 equals k, and then you can bring that in for a square root. So you can go ln of 2 equals k. So for this thing, we end up with at equals AO times e to the ln of 2 multiplied by t. Right, so that's literally the only one you need for exponential growth in k. The only fiddly thing is figuring out k, and all you need to do that is any 2 points. Right? It's just like a straight line essentially, because you've got this guy's going to be a constant, these two are going to be, these two are your variables x, y, and then that's your unknown. Right? Or alternatively, you can think of it in terms of, think of this guy as kind of like c, and this guy kind of like m, from y equals mx plus c. If you've got 2 points on a straight line, you know where the line is. Right? Same thing with this. If you've got 2 points on this curve, you can figure out what A, O, and K are. Yeah? Yes, no, maybe? Yeah? Yeah. The best thing about this, you don't even have to know if it's growing or shrinking. You just run the numbers, right? If it comes out as K is negative, then it must be shrinking. If K is positive, it must be growing. Highly, highly recommend, read the scenario, think which way it should be going before you even do any calculation. That way, if you, when you get your number out, you can go, does that feel about right? Cool? Right. I'll think about that for a second, I'll figure it out. I don't want my brain's failed me, but I'm getting old, so that'll happen. And I've forgotten which chapter is this up. Ooh! That's five. 5G is also on the list of stuff. That's just inverting between e to the power of and log base e. So you just find inverse graphs. We've done that already. We just haven't done it with e specifically, so I'm just leaving that as homework for you guys just to knock out because it's not new stuff. It's old. Yeah, this stuff is more new, but this is all worded stuff, or pretty much all worded stuff. So I just want to read, think, apply. Yep.
All the stuff in the right.
That red formula we'll use for anything that is exponentially growing or decaying. You can always use that way. I'm just trying to make people appreciate it by writing all the other ones and then going, you don't need it, you just do that.
So we don't have to remember all other.
No, don't need any of the rest of them, just the red one. Oh, beautiful. Alright.